In this lecture, we will talk about how to build the status stresses for our various cases. Before we do that, we need to talk about what are the stress concentration factors that we use in fatigue. Okay, in fatigue, we use what we call notch sensitivity. And the notch sensitivity we express it with letter Q. We'll talk about that factor in a minute. So, it, so regardless if you're working in for brittle materials or ductile materials now, so you remember when we did static loading, let me just write this down here, brittle, ductile, and brittle. Okay. So for static, when we were doing static analysis, I told you to take your KT equal to 1, right? A, KTB equal to 1, KTS equal to 1. And the brittle, you found this from the tables. Right? This came from tables. Now, this is true for only static loading. Okay. Now, when we have fatigue, things are different. In fatigue, what you will do is now for both cases, you need to find your KT. So you find your KT regardless of the material that you're working on. Okay, so you will find this is not equal to 1 here. It's not equal to 1. And this applies both, applies in ductile materials and applies in brittle. Okay, so you will use tables for this, the same tables that we have been using from appendix A. Okay, using those tables, you can find your stress concentration factors. Now, once you find your static stress concentration factor, I want to reiterate, when we did this in static, we assumed this is equal to 1, and for brittle, we found this using from the table. However, when we work in fatigue, you need, regardless if it's ductile material or brittle material, you have to go to the tables. It's not equal to 1 anymore. Okay, and what we do is we want to find a reduced stress concentration factor. Okay, and this reduced stress concentration factor is KFS. It will be KFS if you're working in for torsion, or let me write it down like this. For torsion, you have KFS will equal to 1 plus QS KTS minus 1. For axial, it will be KFA equal to 1 plus QA QTA minus 1. And for bending, it will be KFA 1 plus, B, KB, KTB minus 1. Okay, so this is your reduced stress concentration factors that we are looking for in fatigue. These are the ones that we care in fatigue. This is your notch sensitivity. Notch sensitivity. And these values over here are your static stress concentration factors. Okay, these are your static stress concentration factors. concentration factors. Okay, and these factors again come from your appendix A. So what happens is when you look at your fatigue, in the case of fatigue, you have a structure that's doing like this constantly, right? And so it doesn't allow it to fully develop your entire peak stresses. So you constantly, when you think you're going to develop your peak stresses, you are collapsing, and then you expand, and you collapse, you expand. So you're constantly applying that, and what you see is that you just doesn't completely apply it. So you have a reduction. There is no need to put extra burden on the structure. When I say burden, I'm talking about adding, it's like adding an additional factor of safety that's not needed. Uh, so the stress concentration factor we use is reduced stress concentration factors. Now, the different way we apply this, both for brittle and for ductile and brittle, we have different ways to apply it for alternate. What happens in alternate stresses and what happens in mean stresses. Okay? Now, the easiest thing to understand is what happens in alternate stresses. In alternate stresses, you will always assume that your F, that you're going to use a KF, okay, and I'm going to be kind of crazy here. This is KF as A as an alternate. You're going to use your KFA. Then when you use your KB, okay, we're going to call it alternate, A as in alternate, and use KFA. And then KFS, and this is alternate. So you're going to say this is the same as, sorry, this is B, and this is S. Okay, this is what you will get from the tables from these equations. Now, mean, how you work in mean is a little bit different. Okay, this you will apply for both, regardless if it's brittle or ductile materials. Okay, it doesn't matter what type of material you're using, you're going to take this reduced stress concentration factor and you will and you're going to say that's going to be alternate. So that means that your alternate stresses will use that. Now for mean, let me go to the next table, next chart. If you are working in, or let me actually stay here. For brittle is very easy. For the case for brittle material only, you will just use the same. Okay, so you have axial, bending, and torsion. We're going to use the letter M to identify this as mean, because they have different for each case, and you're just going to use the values that you get from the charts, okay, that we got from the previous equations. Okay, so you can see that for the brittle case, these two are identically the same for alternate and for the mean. Okay, now for ductile, only the alternates are the same, but the means are a little bit different. How we work with this are various cases. So I am going to create for ductile materials, okay, KFM, okay, is different. And we got three case scenarios. One, case two, case three. This is the conservative approach. Again, conservative means that you're putting an extra burden to the structure, and your structure will be thicker. Okay, that you're going to have more size. You have to put a stronger material in picture. And what we do here in this case is we say we want to put all the KFAM equal to 1, KFBM equal to 1, KFSM equal to 1. Okay, so this is a conservative approach. Just assume it's equal to 1. The typical approach is the following. This is the one that we commonly use. We just assume just like the case for the brittle case, we assume that the values that you get from the charts, that's the value that we'll use. I know that you're wondering where I get those values from. Just hold on to that thought for a moment. We will get to that. KFS mean is KFS from the charts. The other approach is this is the non-conservative approach. Okay, and this approach consists in the following. For all three cases, okay, you're going to use what your book calls the following. This method was mainly developed by Dowling, and this is equation 6.39 of your textbook. And there are three cases, and I want you to follow your textbook. The first case says that KFM will equal to F. Actually, let me go ahead and work this particular case on your next page. Okay, so let's go to your next page, and I just need more space. For the non-conservative case, and again, this is for ductile materials. Okay, we are just expanding here, just need more space. So KF is going to equal to KF, what you get from the tables. Okay, if KF absolute value of sigma max, this is nominal, okay, less than sigma yield. Okay, so if this is true, then you use this factor. Otherwise, you're going to make this equal to sigma yield minus KF, sigma alternate, sigma mean. And these are the stresses that you get without applying any factors. So you find KF sigma max. This is bigger than sigma yield. Okay. The last case is take this actually equal to 0, and you have the following case: sigma max minus sigma minimum has to be bigger than 2 times sigma yield. So these are the three criteria. And for the purpose of this book, we don't actually, this course, we don't recommend this method at all. We recommend that you use one of these two methods. However, for your homework, there is an exercise that we want you to go through this. And yes, you have to do all these three cases. You have to do these checks for axial separately. You have to do it for bending separately. And you have to do it for shear separately. Okay, just remember when you're working with shear, in the case of shear, wherever you have sigma yield, you have to use sigma s. Okay, for the case for shear, use this, and this will be sigma yield divided by square root of 3. That will be your sigma, the sigma shear that we will be using in the problems. Because in those cases, the case of pure shear, so then you really have tau A, you have tau M, and you have tau max, and you have tau minimum. Okay, so where you replace all these values just for this, in the case only for shear. Okay, so how do I find? So we know from the charts how I find this, right? We already did this in the previous topic. Now, if I knew this, then I can find this. And this is very easy. This is found from your charts, 626 in your textbook. And what you do is you can come here. This is good for bending or axial loading, okay? And this is steels. And these are different plots for the case of, I'm sorry, these are for steels and this is for aluminum alloy. So if you have the notch radius, when I talk about notch radius, we are talking about this radius right here. This is your R. Or maybe for the case of your previous homework that maybe it looks something like this, then this is your R, right? Depending on the R in the case that you have from the chart, from the appendix. This comes from the appendix, okay? From your appendix. Then you use this value here, and then you will just go up here, depending if it's aluminum, just go there and find a value that gives you Q. You can see that you will use the same Q for QB and QA for this particular case for steel and aluminum. Now, if you're working, I'm sorry, for aluminum, if you're working for steel, then you have to look at the value of your ultimate tensile, right? If your ultimate tensile, let's say, is 80, then you're talking, okay, it's more or less somewhere here in the middle. Then you just go there in the middle and you find a value. Okay, so all eyeballed approximation. Now, this is for only torsion loading, so this is what we call QS. And it's the same thing, right? You have your radius, and you find your radius and you find a value of Q. Again, this is for aluminum. These are for steels. There are other ways to find this. This is how actually the computer, my computer code does it for you. Your computer code does it for you. So, but this is the notch radius. This value right here, I'm going to give you, I will tell you what it looks like in the next chart. And then, or you can actually express the whole thing like this. But if you have the Q, and what is the Q? Well, it's given by this equation right here, okay? So this Q is given by this equation. This is what your computer code does. But if you want to do it by hand, you just go here, find a value, you move on. Okay, this is the chart that you always use. These two charts are the main charts that you're expected to be using. Okay, but for programming purposes, it's a lot easier to use this. And you can see you got different charts for different ranges of your ultimate. Same for torsion, you get different ranges for your torsion. And you can use that. Now for the case for cast iron, then we just recommend use Q equal to 0.2. Okay, that's for mainly for brittle materials. So now that we know what your stress concentration factors are, then you need to go ahead, you need to do the following. You need to multiply your alternate with the alternate, sigma xx, axial, okay? And you will divide this by what we call a load factor, okay? KLA. This is a load factor so the load factor for axial is always going to equal to 0.85. Okay, so this will be your new sigma xxa that you will put in your computer code. Or your computer code is actually asks for this value. So it just doesn't ask you for this value because they're already embedded into the code, and they calculate this by giving, if you give them some value of your loads. Okay, so then your new sigma xx axial in bending, again, this is all in alternate. Then you use this in axial, but in alternate. And this gives you sigma xxb, and is divided by KL. Okay, B. Now, what is your KLB? So for bending, we write it down here in bending. KLB is going to equal to 0.9 if pure bending. If it is pure bending, K equal to B equal to 1 otherwise. Okay? Now, For the case for your shear, right, in torsion, let me put T, and then the shear, alternate. This will give you KFS alternate, and this gives you tau XZ alternate divided by KLS. Okay, for torsion, let's write it down here. For torsion, KLS is equal to it's recommended to use 0.77. This is for pure torsion only. And KLS is equal to 1 otherwise. Okay, so just use this value only if you're working in pure torsion. Now, for the mean, alternating mean, then you don't have any factors at the bottom. You just have Ka mean, sigma XX mean, sigma XXB mean equal to KFA mean, sigma XXB mean. I'm sorry, this is A, but it's alternate, alternate, alternate. And then this is tau XZT mean will give you KFS mean, tau XZ mean. Okay, and you don't have any factors at the bottom. Okay, that's important to mention. So now that we have all this, if I'm going to do this in the next slide, I am going to replace, just note, if it's alternate, right, for the case for alternate, this is actually KFA. This is, this is B. This is KFB. This is FB alternate. This is the same as KFS. Okay, so this is not going to change. What mainly changes is this value, these values. If you're using classical, they're all the same. If you're using conservative, this is all equal to 1 for the mean. If it's non-conservative, then you have to do your rules that we talked about here, okay? So you have to use these. Okay, so your state of stress then will look like this. Your sigma A is going to actually equal to sigma FA, sigma XX axial alternate divided by 0.85, because that's the load is always applied, plus FB sigma XXB in alternate divided by KLB. Okay, and then this is going to depend for the various cases. This is 0 and this is 0. This is KFS tau XZ torsion in alternate divided by KLS. Okay, this is 0, this is 0, this is 0, this is KFS tau XZTA KLS. And as you can see in this problem, now the only thing that changed from what we did in the past, that we have these extra factors that we didn't have before, right? And we have to do this again. These are the new factors that are in the problem, and we have to do this for the alternate stresses and for the mean stresses. And from here, from this, I'm going to build a new sigma 1a. I'm going to solve my my principal stresses problem, find the principal stresses of my modified stresses. Okay. Now, if you're working for the case in which the second state of stress, sorry, it is the mean state of stress, and the mean state of stress is actually equal to following: is KFM. Okay, it's not too much complicated there because it's all in mean. We don't have any load factors applied here, so this is A mean, B mean, sigma XX B mean, 0 KFS mean, or actually this is, we don't need to put mean because they're all the same factors. Well, we should. It all depends on every case that you're working on, right? If you're working brittle, it's different, and the approximations are different. So this is torsion B. This is 0, 0, 0, 0, 0. KFS mean, tau XZT mean. Okay. And from here, you're going to build your state of stress, and you're going to find your principal stresses now on this state of stress, which we already learned in the past, right? So before we move on, and the next question is, what do we do? Well, we need to really find what are the stresses that we're going to use. So if you recall last time, I told you there are different ways we do that, right? So I am going to divide this, okay, for ductile materials and for brittle materials. Okay, so what we really care for here is we want to find what your SA will be. Okay, your SA for brittle materials, you got two options. Either you can use sigma 1A, or you can actually find your von Mises. Okay, sigma equivalent alternate, and that can be your SA. Now, for your mean, you can do the same thing, right? If you use alternate, if you're going to use this, then you're going to use that. You're going to use the, if you use this, you use this, okay? You cannot combine this with this. Sigma equivalent mean with sigma alternate. Now, for the brittle material, we don't have a problem because we are going to set this equal to A, your principal stress, and sigma M to your equivalent, for your principal stress, maximum principal stress, sigma 1. Okay, then from here, what we really want to do, once we have the sigma SA and SM, you want to decide what is your S maximum. Okay, your new S maximum is alternate plus, or I like to write a mean plus alternate, and your minimum would be sigma mean minus alternate. Okay, so now you have these two new cases, and these are the stresses that we're going to use as we move forward. Okay, so just as a summary, the only thing that we are doing different from the static case, we have to actually find your reduced stress concentration factors, okay? And this reduction is actually a help for fatigue. And by using that, we need to, with this we know from the static problem, the knot sensitivity is here. And to do the knot sensitivity, then we went to these two charts, one of these two charts to find your Q. And then I multiply this times this, and you can see if this is close to 1, this becomes a very small number. So this number in general, this number, your KF, I should write this down here, your KF is always going to be less or equal than your KT, and it's going to be bigger than 0, okay? So bigger than one, I'm sorry, bigger than one. So you have to keep this in mind. They're all always bound by these two values. Okay, they're bound by KT and 1. They also can be equal to 1 if your Q was actually equal to 0. So this is what we have. And then if you, once you did that, for the case for brittle materials, alternate was not a problem. It's the same for both cases. For mean, well, brittle this is the case that you work with. And then ductile materials, you had two cases. It's typical where we just use this both for both ductile and brittle. This is a conservative approach. This is a non-conservative approach that's a little bit more complex. And this is bound between, don't forget, 1 and KT. This is KF. And then from there, what you're going to do is you're going to build your state of stress for alternate, and you have to divide by your loading factors. Remember, the 0.85 is always there. This is regardless if it's ductile materials or yielding, okay, or brittle materials, sorry. And then for the mean, you just don't have any divisions here, so you just use this as is. From here, you find your principal stresses. And for ductile materials, you have two approaches. You can either use principal stresses or von Mises stresses. And then for brittle materials, you just use the principal stresses. And then you find your sigma max and sigma minimum. Those are the stresses that we'll use as we move forward.